So this is Dr. Sweeney, and what we're going to be looking at today is we're going to be looking at something called the First Shifting Theorem for Laplace Transforms. Now, the First Shifting Theorem is going to expand the number of functions that we can use in order to create Laplace transforms and then find inverse Laplace transforms of. And so that'll actually allow us to solve differential equations or initial value problems for more kinds of differential equations. So it ends up being really, really handy. Since this is a theorem, what we'll do is we'll start out with the actual statement of the theorem. And so the first shifting theorem says if the Laplace transform of f is equal to big F of s, right, just standard notation there, then the Laplace transform of e to the t f of t, so that is if we multiply f by some exponential function with a constant value a, is going to equal big F of s minus a. And that's actually the shifting there, right? What we're going to be doing is we're going to be shifting to the right by a units the Laplace transform. And if the Laplace transform inverse of big F of s is equal to f of t, then the Laplace inverse of big F of s minus a is going to equal e to the at f of t. All right, so basically, if we've got this Laplace transform, its inverse is exactly what we should expect it to be. Its proof follows directly from the definition of the Laplace transform. So what we're going to do is we're going to take the integral from 0 to infinity, and what we'll get is we got e to the at, and then it'll be e to the negative st f of t dt. So this is that part for f of t, and then this is the e to the at, which we're just going to be multiplying by. If we bring that in, we're going to go from 0 to infinity, and this is going to be e to the, and it'll be negative s plus a of t f of t dt. And that'll then equal the integral from 0 to infinity, and then it'll be e to the negative s minus a t f of t dt. So it's just a little bit of algebraic manipulation within the integral. And what we get here is this thing right here is, by definition, it's f of s minus a. Big F of s minus a, because instead of having s as our variable, instead we're going to be submitting s minus a into the argument of that function. And that's really it. All that we're doing, the entirety of the proof, basically. And so what that looks like from a practical standpoint is we've got the Laplace transform for our function, so it's big F of s, and we'll imagine that it looks like this. So that's the Laplace transform, and then what happens with the first shifting theorem is exactly like I said. We're just going to shift it over a. So this is units, and we will essentially have the exact same function, just shifted over a units. From a graphical standpoint, that's basically what's happening. Now let's talk about what this means from a practical standpoint when we want to go through and find the Laplace transform. Let's look at an example. Suppose that I want to find the Laplace transform of e to the 3t cosine 2t. Now I know that the Laplace transform of cosine 2t is going to end up equaling s over s squared plus 2 squared. That's our standard Laplace transform. So what we'll do is we'll use the first shifting theorem, and what we're going to do is we're going to, in the place of s, we're instead going to use s minus 3. So this Laplace transform is going to equal s minus 3 over s minus 3 squared plus, in this case, 4. And so that's the Laplace transform using the first shifting theorem. Let's take a look at another example. Suppose we want to find the Laplace transform of t squared e to the 3t. Now we know the Laplace transform of t squared is going to equal 2 factorial over s to the 2 plus 1, or cubed. What we'll do is then we're going to substitute in, okay, the 3 in there as an s minus 3. So this Laplace transform is going to equal 2 factorial over s minus 3 cubed. So instead of s, we just have s minus 3 cubed. And that's all we've got to do for the first shifting theorem. In fact, if we wanted to think about this, we could create a set of Laplace transforms where we just adjoin or we just multiply our functions by e to the at. So for example, if I wanted to find the Laplace transform of t to the n e to the at, what that would look like is that would look like then we'd have n factorial over s minus a to the n plus 1. Basically, it's going to look exactly like the Laplace transform that we used before. It's just that instead we're going to have s minus a inside it. Now, where I think the first shifting theorem comes in really handy is when we have inverse Laplace transforms. We've got functions that we have the Laplace transforms for, and we need to get back the original function. And it really kind of helps to expand things, and we'll see why. But let's start out with a basic example. Let's say, for example, I want to find the inverse Laplace transform of 6 over s minus 2 cubed. And what I need to do is I need to recognize that what I'm looking at right now is I'm looking at one of the form of like t to the n. And so I've got here that this is basically, if I had n plus 1 equals 3, then n is going to equal 2. So what I have here, or what it looks like I have, is I'm going to get the Laplace transform of t squared, which I know again is going to be 2 factorial over s to the 2 plus 1, okay, which is that cubed. Now, if I look here, the 2 that I have in there, that's going to be my a. So a is going to end up equaling 2. And so we're going to add that in for that first shifting theorem. And then the one other thing that I need to get is that notice that this is a 2 factorial ends up equaling 2. So that's not what I have on top. Instead, I have 6. So I'm going to have to pull out 3. So basically what I'm going to get here is I'm going to take 3 times the inverse Laplace transform of 2 over s minus 2 cubed. And now I have it of the right form that I need. And so that's going to be 3. And then it'll be e to the 2t. That's where this 2 comes in, e to the 2t. And then this will be t squared. If I rewrite that, I've got it 3t squared e to the 2t. And that, in fact, is the inverse Laplace transform for 6 over s minus 2 cubed. So now let's look at another example where it doesn't look like we're using the first shifting theorem, but in fact we are. So we want to find the inverse Laplace transform of s minus 2 over s squared minus 4s plus 20. So if I think about this, what I'm really looking at here is I'm looking at some kind of cosine function. So if you remember the inverse Laplace transform, of, say, s minus a over, and we'll call it s minus a squared plus b squared, is going to end up equaling e to the at cosine bt. So using the first shifting theorem, we'll end up having our e to the at. And then also what we'll also have is we'll have our b squared for that cosine bt. So how would I actually go about changing this such that I can get it into this form right here? And so all it really takes is it just takes a little bit of a trick. So what we're going to do is we're going to separate this out. I'm going to get L inverse, and this is going to be s minus 2 over, and I'm going to complete the square, or I'm going to divide out 2 pieces in order to complete the square. So I've got s squared minus 4s, and then plus 4, and then plus 16. So I'll separate out my 20 into 4 plus 16. If we notice here, this is going to end up being s minus 2. So this will be the inverse Laplace transform of s minus 2 over s minus 2 squared plus 16. So a ends up equaling 2 and b ends up equaling 4. So this implies inverse Laplace transform ends up equaling e to the 2t cosine 4t. And so you can see that that modification allows us to utilize this first shifting theorem in order to give us our inverse Laplace transform. So let's now go out and solve a problem that without the first shifting theorem would have actually been a little bit difficult, but now is quite simple with the first shifting theorem. If we look at the inverse Laplace transform of 6 over s minus 1 times s plus 2, the issue that we have once using partial fractions is this s minus 1 squared term. We don't have a simple way without the first shifting theorem to go out and find the inverse Laplace transform of it, and so consequently this would be kind of difficult. But now with that first shifting theorem, it's not going to be so bad at all. So the first thing we want to do is use partial fractions in order to go out and split up this function into 3 component parts. So 6 over s minus 1 squared plus is going to end up equaling negative 2/3 over s minus 1 plus 2 over s minus 1 squared plus 2/3 over s plus 2. So now what we have to do is we're going to go find the inverse Laplace transform of each one of these. So the inverse Laplace transform of negative 2/3 over s minus 1, the inverse Laplace transform of 2 over s minus 1 squared, the inverse Laplace transform of 2/3 divided by s plus 2. This first one is going to end up being negative 2/3 e to the t. And we have that's their standard Laplace transform. Then plus, and then this one's going to be the one where we use the first shifting theorem. Notice that we have a squared term, so our a here in this case is going to end up equaling 1. And this is going to be t to the first power. And that's because, right, s to the n plus 1. So n is going to end up equaling 1. So this term is going to end up being 2 e to the t. And the e to the t comes from the s minus 1 in there. Then the third term is going to be plus 2/3, and this will just be e to the negative 2t, just like our standard Laplace transform. So consequently, what happens here with that first shifting theorem is it makes it a lot easier for us to split up our Laplace transforms into component parts using partial fractions, and then find these individual values, particularly here when we have, like, say, for example, linear terms. So now let's go in and find the inverse Laplace transform for something a little bit more complicated. So what we've got here is we've got 2s plus 4 over s times s squared minus 6s plus 13. The issue previously before the first shifting theorem would be that s squared minus 6s plus 13 term. But using partial fractions, we're actually going to be able to separate out those two terms, and then s squared minus 6s plus 13 is going to be something that we can then find an inverse Laplace transform for. So let's first go in and use partial fractions in order to figure out what 2s plus 4 over s times s squared minus 6s plus 13 is. After using partial fractions, what we get is we get 4 over 13 over s plus negative 4 over 13 s plus 48 over 13 divided by s squared minus 6s plus 13. Now, for the sake of simplicity, for just a moment, I'm going to go in and I'm going to transform this into a form that I can use the first shifting theorem for. So in other words, s minus something squared plus another term. So s squared minus 6s plus 13 is going to end up being s squared minus 6s plus 9 plus 4, and that'll be then s minus 3 squared plus 4. So that's going to be our new denominator there. So that's where that's coming from when I put it in. So now I'm going to take the Laplace transform. My original one is going to end up equaling the Laplace transform of 4 over 13 divided by s plus the inverse Laplace transform of negative 4 over 13s plus 48 over 13 divided by s minus 3 squared plus 4. This term right here, what that's going to end up being is that's going to be 4/13. And what we have there is we'll pull out the 4/13 from our original Laplace transform, and then the Laplace transform, inverse Laplace transform for 1 over s is just 1. Now, the trick here is to do the inverse Laplace transform here for our second term. So this is going to end up being plus, and what I'm going to do is I'm going to pull out negative 4 over 13 in order to simplify that top part. And that'll be negative 4 over 13 times the inverse Laplace transform of s plus, or s minus 12 divided by s minus 3 squared plus 4. Now notice I have an s minus 3 down here, and in order to use cosine, the inverse Laplace transform of, in this case, s minus a over s minus a squared plus b squared, that's going to end up being e to the at cosine bt. I'm going to need to actually separate out the s minus 3. So this is going to end up equaling, and I'll just look at this term right here. I'm just going to do the second term. We'll add the 4/13 in later. This will give us now negative 4 over 13, the inverse Laplace transform of, and we're going to have s minus 3 over s minus 3 squared plus 4. Our last term then is going to be negative 4 over 13, because that's that coefficient, inverse Laplace transform, and this is going to be negative 9 over s minus 3 squared plus 4. The reason why we'll do that is because you notice that s minus 12 is simply s minus 3 minus 9. So that actually allows us to do what we need to do. Now take a look up here at this formula up here. The Laplace transform of sine bt is going to equal b over s squared plus b squared. What we want to notice is that even with the first shifting theorem, this isn't actually inside of that form. So what I'm going to need to do is I'm going to need to change my -9 into what would be. Now b in this case is going to end up being 2, because 2 squared is 4. So what I'll do at the end here when I do this is I'm going to multiply by -2/9, and then that'll give me the 2 that I need in order to find the sign. So what I get now is I'm going to get 4/13 minus 4/13, and this term here is going to end up being e to the 3t cosine 2t, and then this will be minus 4/13 times -2/9 e to the 3t sine 2t. And that ends up being your inverse Laplace transform. That's the function that we're looking for, little f of t. So what you can see here is that we'll actually use a combination of our partial fractions techniques, right, and this first shifting theorem technique in order to go out and find the inverse Laplace transform. So now let's talk about some key techniques and ideas that we got here from the first shifting theorem. One thing is that the first shifting theorem allows us to have essentially 3 new functions that we can find Laplace transforms for quickly. So we have the Laplace transform of e to the at sine bt is going to end up equaling b over s minus a squared plus b squared. The Laplace transform of e to the at cosine bt is then going to equal s minus a, okay, because we'll plug in the a, times s minus a squared plus b squared. And the Laplace transform of e to the at, call it t to the n, is going to end up equaling n factorial over s minus a to the n plus 1. Couple things to note here is we want to note that in each case, okay, for both the sine and the cosine, for example, we have this plus b squared. And that's actually going to end up being really important because that's going to restrict the number of things that we can actually find the inverse Laplace transform for. It'll also restrict as to whether or not, like say for example, we have to a 4th power or a 6th power. We're going to need that our last term, okay, inside of the denominator of anything that we find the inverse Laplace transform for, be a plus sign. And not just a plus sign, but a specific kind. So let's take a look at an example and to see what I'm talking about here. So let's say, for example, I have s squared plus 10s plus, and say it's 35. Now, what we know is that we're going to take this, we're going to make this s squared minus 10s plus 25 to give myself the perfect square, and then plus 10. So that's going to end up being s minus 5 squared plus 10. That's great. I can actually go in, and if I saw that in the denominator, I can make some changes to my functions in order to actually find an inverse Laplace transform for something with that in the denominator. However, if I have something in the form like this, s squared minus 10s plus 20, what you'll see is that this is now s squared minus 10s plus 20 minus 20, plus 25 minus 5. So this is s minus 5 squared minus 5. Well, notice there's no way, I mean, unless we're using like complex numbers, to make that b squared into that -5 that we need. And so consequently, we wouldn't actually be able to use this first shifting theorem for that purpose. Or, for example, if we have something like this, s squared minus 10s minus 38. In that case, what we get is we get s squared minus 10s plus 25 minus, and now we'd have to add 25 and 38, so that's 63 minus 63. So this ends up giving me s minus 5 squared minus 63. And again, notice we have a plus b squared, a plus b squared, and it would certainly not a perfect square of any form. And so consequently, we can't utilize the first shifting theorem in this case. All right, the form isn't correct. So you want to make sure that you can, in fact, make this transformation in order to utilize that first shifting theorem. So something of this form where if you take the s term, divide it in 2, and square it, it's actually less than or equal to whatever that last constant is. All right, and that'll allow us to, in fact, use the first shifting theorem. This is Dr. George Sweeney, and I want to thank you for watching my video. If you found it helpful and you liked it, go ahead and click the thumbs up. If you want more of these videos and you want to get my updates, please click subscribe. If you have any questions or you just want to say how much you really enjoyed the video, go ahead and leave some comments. I do read and respond to the comments.